Welcome, Honors Physics students. Let's consider a one-dimensional kinematics problem. Suppose Mr. Wilson is standing atop the Burj Khalifa, the tallest building in the world. The height of the building is 2,720 feet, and Mr. Wilson is looking over the edge. He throws a golf ball straight upward, released from an initial height of 831 meters above ground level, with an initial velocity of positive 20 meters per second. And the golf ball just misses the building's edge as it falls towards Earth's surface. Answer all of the following questions. A. How long does it take the ball to reach its maximum height? B. What is the ball's maximum height relative to the ground? C. How long does it take the ball to reach the ground? D. What is the ball's velocity when it hits the ground? And E. What is the ball's position and velocity at t equals 5 seconds? Please take a moment, pause the video, and try your very best to answer all 5 of these questions. When you've attempted all the problems, check your answers with mine. The first thing I always recommend for a complex problem such as this is to draw a picture. In this picture I've drawn, I've carefully labeled all of the physical information necessary to solve this problem. I note that the displacement of the ball once it reaches the ground will be negative 831 meters because I choose to set the initial position, the position where Mr. Wilson initially released the golf ball, equal to 0. Notice that I've also labeled the initial velocity to be 20 meters per second in the upward direction, and since the velocity is upward, we should expect the time that it takes for the ball to reach ground level to be longer than it would have been had we simply dropped the ball from rest. Once the ball leaves Mr. Wilson's hand, we can consider it to be a freely falling object, and all freely falling objects near Earth's surface experience a gravitational acceleration equal to negative 9.8 meters per second squared, or meters per second per second. Perhaps you're asking yourself, what does it mean to have an acceleration equal to negative 9.81 meters per second squared? Well, you might want to pause the video at this point and carefully analyze the velocity versus time graph that I've created. If a freely falling object has an acceleration equal to negative 9.81 meters per second squared, that means that its velocity will decrease by 9.81 meters per second for every second that the object is in the air. In other words, the moment that the ball leaves Mr. Wilson's hand, it has the instantaneous velocity equal to exactly what he threw it at, which in this case is 20 meters per second. Exactly 1 second later, the ball's velocity will decrease by 9.8 meters per second, which means that the instantaneous velocity of the ball 1 second after Wilson threw it is now 20 meters per second minus 9.81 meters per second, or about 10.19 meters per second. 2 seconds later, the ball will have an instantaneous velocity of 10.19 meters per second minus another 9.81 meters per second, or 0.38 meters per second. Notice that the velocity of the ball at t equals 2 seconds is very close to 0. This means that it has almost reached its maximum height, and it's about ready to start falling down towards Earth's surface. In fact, if we look at the velocity at t equals 3 seconds, we see that the velocity is now negative 9.43 meters per second, which means that the velocity is now directed downward towards Earth's surface. In other words, the ball is now falling downward rather than rising upward in the air. Let's answer question A. If we want to know the time it takes for the ball to reach its maximum height, we should first make a very important inference that my velocity versus time graph may have helped you realize. Just before the ball reaches its maximum height, it will have a very small positive velocity. Just after the ball has reached its maximal height, it will have a very small negative velocity. At the maximum height of the ball's velocity is exactly 0. That is a key to solving this problem. Now that I know the ball's initial velocity is equal to 20 meters per second, as my picture shows, the rate at which the ball's velocity is decreasing is 9.8 meters per second, and its final velocity is equal to 0, I can simply use the kinematics equation Vf equals Vo plus At to solve this problem. Let's substitute in all of the physical values that I know, and this will allow us to solve for the time it takes for the ball to reach its maximum height. At this point, I can move the 20 meters per second to the left-hand side of the equation by subtracting 20 meters per second from each side. And at this point, all I have to do is divide by the acceleration due to gravity on each side of the equation, and I will have the time it takes for the ball to reach its maximum height. Now to address question B, what is the ball's maximum height relative to the ground? We should probably use our answer from question A, and that'll make this problem rather simple. Since we know the time it takes for the ball to reach its maximum height, we can use that time in another one of our kinematics equations to calculate the maximum height of the ball. Of course, we need a kinematics equation that has displacement, so this is the equation I think is most appropriate. Keep in mind that I chose to call the release height 0. As you can see, the maximum height will be the highest height above the release point that the ball reaches. Let's solve for delta x, since we know the initial velocity, the time, and the acceleration. As you can see, I've inserted all of the numerical values into the equation for the variables that they represent. And at this point, all I have to do is get my calculator out and solve for delta x. I trust that you know how to work your calculator, and please do this as we go along, but you should get delta x equals 20.4 meters. But please reread the question and notice that we want the ball's maximum height relative to the ground. The height that I've just solved for is the height relative to the height that Mr. Wilson initially threw the ball, meaning that if you look where I'm highlighting where the ball's at, the ball has gone 20.4 meters to reach this height right here. Now that height, 20.4 meters, must be added to the height of the building. Therefore, the ball's maximum height relative to the ground can be stated as delta x equals 20.4 plus 831 meters. This value to three significant figures should give you a maximum height for the ball of 851 meters. From that height, the ball is now going to fall 851 meters in the negative direction down to Earth's surface. So for part C, how long does it take the ball to reach the ground? You can actually approach this problem in two different ways. One would be to use the quadratic equation. I've done a few steps at once, but because the ball's position is going to be 831 meters below where Mr. Wilson initially threw it, you could set this equation up as negative 831 for delta x equals the initial velocity of 20 times time minus 1/2 times negative 9.8. I've simplified that to be negative 4.9 times the square of the time. However, we could use a second method if you aren't a big fan of the quadratic equation. If you don't mind the quadratic equation, simply go ahead and solve that. But because I've already solved for the time it takes for the ball to reach its maximum height, as I'm going to show you over here, we know that time it took was 2.04 seconds. So since I know the time it takes for the ball to get to its maximum height is 2.04 seconds, I could simply find the time it takes for the ball to go from its maximum height here all the way to ground level, and then add that to the time it took to get to the top, and that would give me the total time it takes for the ball to go from Mr. Wilson's hand up to its maximum height and then all the way down to ground level. One nice thing about this approach is that the velocity of the ball is 0 meters per second at the maximum height. So if I use the kinematics equation, delta x equals VOT plus 1/2 AT squared, I can essentially cancel the V naught T term or the V sub OT term because the initial velocity is 0. If the initial velocity is 0, 0 times time is of course going to give you 0, so the V naught T term cancels out, and all we're left with is delta x equals 1/2 AT squared. I can't stress this enough. The reason I'm using negative 851 meters is I am considering the displacement from the top of the trajectory here down to ground level. It is 831 meters from where Wilson threw the ball to the ground, but remember, the ball reached a maximum height of about 20 meters above his hand, which is why I'm using 851 rather than 831 for the displacement. And of course, I have to use negative 851 because the ball is going from an extremely high height to a height way, way down below. And we typically call the negative y direction down towards Earth direction. Let's now substitute in our value for the acceleration due to gravity. And if we just simply take half of negative 9.8, our equation will end up looking something like this. All you have to do at this point is simply divide both sides by negative 4.9. And of course, a negative divided by a negative should give you a positive, and that makes sense because when we take the square root of both sides, you cannot take the square root of a negative number. Therefore, we should expect to get a positive number on the left-hand side. And what we end up with is t squared equals 174. And if we simply take the square root of both sides now, we will see that t equals 13.2 seconds. But be careful, that is not the time it took for the ball to go from Mr. Wilson's hand to ground level. All you've calculated is the time it takes for the ball to go from its maximum height to ground level. So using your approach, you must also remember to add back the 2.04 seconds it took to go from Mr. Wilson's hand to the maximum height, and that will give you the total time for the ball to go from Wilson's hand to the maximum height, and then all the way back down to the ground below. I obtain a final answer of 15.2 seconds for the entire process of the ball going from Wilson's hand to the ground in this situation. One last note I'd like to make about the way that I chose to solve this problem. Note that for the application that I did, we can actually set the initial velocity equal to 0 because we were only concerned with the motion of the ball from the maximum height until the ball reached the ground. By breaking the problem into two distinct parts like I did, I avoided using the quadratic equation. But please don't shy away from using the quadratic equation. It's an extremely powerful equation describing the position of the golf ball as a function of time for any possible time that you could imagine. So, what's the ball's velocity when it hits the ground? To calculate the ball's velocity when it hits the ground, we should use the time we've determined for the ball to hit the ground and simply plug that value into our equation v equals v naught plus at. Because I know the time it takes for the ball to reach the ground from part C, the only thing I have left to solve for is v sub f, because I know v sub naught, I know the acceleration due to gravity, and I now know the time. So let's plug those values in. As you can see, I've plugged in the initial velocity of 20 meters per second. The acceleration due to gravity is negative 9.8 meters per second, and the time of 15.2 seconds. To solve the problem, all I have to do is a very quick calculation, and I will determine the final velocity. I've obtained the final velocity of negative 129 meters per second. And that is about negative 289 miles per hour. That is extremely fast. Now the question is, will the golf ball be falling at 289 miles per hour when it hits the ground? We will have to actually wait until I get to Chapter 4 to talk about things such as air resistance, friction, and forces causing acceleration before we really delve into that question. But that is indeed a very good question to consider. And finally, what is the ball's position and velocity at time t equals 5 seconds? The ball's position can be determined using this kinematics equation. Obviously, I had to choose a kinematics equation that had position in it, and delta x, sure enough, would give me the position of the ball relative to Wilson's release point. So let's plug in all the stuff that we know from the problem, and this is what it looks like, minus a few of the units because I was short on room, when I put in all the values. I trust that at this point you know how to use your calculator. The first part's easy. Simply take 20 times 5 to get 100. And in the second part, I would start off by squaring the 5 and then multiplying that value by negative 9.8 and then taking half of whatever number that was in your calculator. It should look something like this. Don't forget to watch your units because the units for displacement are meters, so I should state my final answer to three significant figures as negative 22.5 meters. So what about the ball's velocity at time 5 seconds? We can use our other kinematics equation that gives the ball's velocity as a function of time. And if we simply substitute in everything we know, the velocity at 5 seconds equals 20 plus negative 9.8 multiplied by 5, which equals negative 29 meters per second. What this tells me is that 5 seconds after Wilson threw the ball is now 22.5 meters below the height at which he initially threw the ball, and the ball is moving at negative 29 meters per second in the downward direction towards the ground. Okay, that concludes all the parts of this problem. I hope that this video is helpful. Thank you very much for watching. Please share this video with your physics friends, and if you have any additional questions, please feel free to stop in and see me before or after school.